This is just like a photo, just print it out. Yeah. Oh, yeah. Seeing the email chain, but if I send.
He should have said, it should have given you a specific one, because you weren't on there earlier. And so added you that. So you might have gotten the second one.
Okay.
So whichever, do you have an Airbnb account?
No.
One, two, you drop, and since the substrate is hot, count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See it from here, it becomes water. And
Okay, yeah, it's
it doesn't bubble.
okay. Yeah, I need
It's-
a
It's
lower
like,
heat source then, because like when I drop it on, I mean, it instantly just like starts turning black and like then it starts to.
then you can
shortly
let
after.
it cool and maybe measure temperature.
I tried that, but it melts the temperature probe. So
Let it cool and measure temperature again. Probably it's too high.
You melt and wow.
yeah, well, like the coating around the actual probe, I guess, but I figure I probably shouldn't be using that if it like starts to melt the thing freaking instantly.
Do you know what temperature this temperature one's?
So what
Really
were they adding? So
Not like
the substrate that was in the glass bowl.
I can like
What was
do
that?
that,
But
you know.
You know what the oven's using?
it's not a simple
hot, like-
substrate.
Oh.
Conducting glass, indium tin oxide,
Okay.
with nanostructured titanium dioxide.
I don't know where
on the top,
anything,
and then you deposit this stuff.
So that
There might be something
liquid
else
was
I
the
see somewhere.
lead halide.
I have no fucking
That's what the video was saying.
It's a mix of
You still sick?
methyl ammonium iodide and wet iodide.
Okay.
I think the hot plate's just a piece of shit. Like,
maybe the
Here's the physics.
no, it's the.
Okay, well, thanks for investing your time into the course. This meeting is not very important for your grades. It's only for your curiosity and general education. The most important and the last meeting will be in 2 days, Friday morning. We will run for 4 hours. Well, it's shorter, good. And tonight, whoever needs help in preparing the videos which are required for your presentations, please stop by QVV 132. So, presence of a video in the presentation is considered as the merit grading point. So, video. If you have no idea and no time, then you may replace video with snapshots, but it is less valuable. Okay. So, if you just arrived, there is a one. Can you just lift it so that everyone sees? So there is one proof copy of your reports, papers, combined together in a booklet. So right now is almost the last chance to change things. So let's this copy travel around, and you may mark with red pen if you find your name misspelled or some typos or some last minute corrections. If you plan to do drastic corrections and want to resubmit the whole chapter, contact me in person. But as time ticks, it's less and less probable to change whole thing. Right now, most reasonable is just to make little corrections, and I will find a way to implement them. Do it myself, or asking a grad student to do it, or whatever. For other questions about projects and oral presentations, stop by the evening session. Yes.
Is the order of the chapters the order of presentation?
Yes.
Um,
If you want to switch it, also let me know. Right now, they are ordered logically based on the content and based on the necessity for people to depart. Like I know for sure that Megan wants to depart earlier, and she's either number 1 or number 2 in the list. So if you have something after, let me know. But then we can damage the logical order. Right now it goes like electrons and nuclei only. So electronic degrees of freedom, mixed, and then only nuclei. Nothing is required for now, for today. You just sit and relax, hopefully enjoy. Maybe suffer, but in a minimal level. Just can fall asleep and avoid anything. If you want to make a little bit more of investment into your education and subject that I will cover, you may fill this table. So it's like no grade quiz. Nothing is required, and do not fill it right now. It will be not possible without material that I'm going to present. So it's
I think that like each one has like a different amount of
okay. So what did we cover last meeting? We quickly squeeze. I see the sound. Does anyone join us online?
No, because otherwise the video would be on this.
Okay, thank you. Maybe it's just or echo.
someone hacked into the system.
Huh? Someone in?
I don't know. It's distinctively working.
Well, I just muted the speakers. So, spin. Internal rotational degree of freedom of an electron and some other particles. And for our course and for our future research life, if any, this is a nice system because it is the mathematically simplest object that obeys quantum properties. So it has only 2 degrees of freedom. Therefore, to describe spin, the wave functions are stored in form of 2-component vectors with basis vector size 0, 1, 1, 0, or in Dirac notation. And one can set up all possible operators, and there is a theorem that total number of independent operators for such basis states will be not more than 4. So if you were taking groups and Lie algebra, you may know this theorem.
Not yet.
So it is SU2 continuous group for this system. Oh, okay. So, same as for harmonic oscillator, raising and lowering operators, in matrix form and in Dirac form. And then you can, by combining products of raising and lowering operators, you can get projectors. Here is plus, here is minus, and here another minus and plus, that would contribute to Hamiltonian, to energy operator, or total angular momentum. The sum and subtraction of the weather operators will give an analog of position and momentum. Do not tell it in public, but mathematically it is something that is real, not imaginary, and rotates synchronously. So another thing to recall from last time, if you take these three projections, three expectation values of the three dependent spin operators, and the fourth one is identity, and multiply it by Bohr magneton from this combination of elementary constants, you'll get contribution to magnetization of the system that contains this electron. If you are able to induce a motion of this magnetization and measure magnetization, I'm not telling that take a compass and walk around the electron, but there are ways to measure magnetic field. You will see that both magnetization of a media and spin projections in simplest case perform oscillations where Z projection, which is subtraction of population in alpha spin and beta spin, and X and Y projections, which are subtractions of the weather operators, sum and subtraction, perform the following motion on a globe, on a sphere. So the Z projection doesn't change, and X and Y projections perform circular motion. This is the basis for nuclear magnetic resonance, where the pace of this rotation at constant magnetic field is different for different chemical objects. So it is a way to identify the structure of a system. Maybe not ideally, it's a complementary to other characterization methods, but it is a understanding of this figure is the doorway to NMR. What else is? It's enough about speed. Okay. Suppose we have a molecule, maybe H2 or maybe iodine 2, and there is a dependence of potential energy surface on interatomic distance, right? But I'm going to make drawings for diatomics because they're simpler, but it is something very general. So what is the goal and what is the expected outcome in the next half an hour? The UVV spectra of molecules are very different from UVV spectra of atoms. Instead of very narrow lines, there are broadenings, and these broadenings have specific substructure. Through today's discussion, we will be able to get an idea of the mechanism for forming this broadening substructure of the UVV spectra of molecules. So when you apply light, what happens? Not much. We will come to the idea that it excites system from the ground electronic state to excited electronic state, and in the excited electronic state, the equilibrium position is different. Our equilibrium of the excited electron. Right? So even if you know energy offset of the ground and excited electronic states, the frequency at which light would be able to perform resonance excitation is not equal to the fundamental frequency difference. It does depends on this curvature of the potential energy surface. This is a very general statement for most of chemical systems. So we are going to get a quantitative way to estimate of influence of this little part of the figure of set between fundamental frequency energy excited minus energy ground and resonance in optical sense. I'm not talking about chemical resonance. It's optical resonance, a frequency at which the molecule absorbs light with better pace, with better efficiency. So this little thing, this offset that we are looking at, in many sources it is called nuclear reorganization. Nuclear reorganization. Why it is called nuclear reorganization? Because upon photoexcitation, the interatomic distance reorganizes, and energy also adjusts to follow this reorganization. So we are getting through the concept of nuclear reorganization in transitions between different electronic states. What is light?
Electromagnetic radiation.
What does it mean, electromagnetic? I already wrote it. What is light? Good. I'm following the plan. Electromagnetic, which means there is something electric and something magnetic. So electric is naturally addressed with letter E. And magnetic, by some unknown reason, is addressed with letter B. Which is not very logical, but okay. And if you explore the strength of, you know what is electric field? It is a reason that makes charges to move. Like in electrochemistry, in our circuits of, so most important circuit is cell phone for everyone. There are a lot of them, right? So potential difference creates electric field and makes charges to move. So electric field at a given point of space goes from its maximal value 0 to negative value maximum 0. And electric field changes as well. Well, magnetic field changes as well. And they are, in space, they are orthogonal. But influence of magnetic field on molecules is non-zero but small. So let's forget about it for the next 40 minutes or whatever you will tolerate, maybe 20. So forget magnetic. So what does electric field, when it is electric field that performs oscillations with the frequency of this omega, right, makes to the molecule? What are molecules from the point of view of basic introductory physics? Or from the point of view of those who are interested in optics? Forget about this complicated conjugation, benzene rings. A molecule is either neutral or charged. If it is charged, it will move according to the field. If it is neutral, it will not move. But a molecule may have electric dipole, right? Polar molecule. Then if you have a dipole and you have a field, it will adjust its angle, right? Nature, known objects. And you can set up the energy of interaction with dipole. E or U, E, electric field times dipole. If they are collinear, then the energy has maximal value, and there will be no torque, no force to rotate it. If they are offset by some angle, then there will be the field will make the dipole to rotate until it becomes collinear. We do not need quanta to set up this statement. Next step. How do we can we rigorously define dipole for a molecule? Two steps. Dipole in general and dipole for molecule. Dipole, molecule. Deep is the abbreviation for dipole. It's not like a snap. What's the definition of a dipole? Distance times charge. If you have positive Q and negative Q on a distance L, then your dipole will be Q times L. And if you want to speak it as of a vector, then we need to set that this vector connecting these two charges, right? A little rigorosity. How do we set up a vector if you know position of positive and negative charge? So it's R plus, vector connecting origin to positive charge, R minus, vector connecting origin to negative charge. Then it will be just difference, R minus minus R plus, right? So vector subtraction. I'm not surprised. I was not intending. Now, how can we project this statement for molecules? What will be the R plus and R minus for a true molecule? Or for any molecule? I do not have doubts that you have the answer in your heads, and it just takes time to verbalize it. So, if molecule is composed of positively charged ions, right? We can take an expectation, an average position, an average charge. We can like make a vector from origin to each ion, add them in a vector form, and then divide by number of ions. And then it will be center of mass, center of charge, center of positive charge. Then, if there is an electronic cloud of electrons everywhere, you can also find a center of, not center of mass, center of charge, center of negative charge. So these two vectors for a molecule will be center of negative charge and center of positive charge. If the molecule is non-polar, they coincide. If it is polar, they do not coincide, right? can't write on the screen. So here is the center of positive charge, position of ion with capital, charge of an ion, and then you need to normalize, divide by total number of ions. And if, just for a second, if your electrons are classical, you just sum over positions of each electron, multiply by minus I. So positive and negative, and you subtract them because they have different charges. It will be a vector multiplied by number of charges. Any objections? So nice. No objections. Now, since you were exposed for quantum theory for so long time, you were strong enough to tolerate it. What is the molecule from the point of view of quantum theorists? Or physical chemist is exposed to quantum theory? Well, molecule is Hamiltonian, and upon diagonalizing which, we will have ground state. Wave function of the ground state of a molecule. And ground state of a molecule can be approximately, well, it will depend on positions of all electrons, many electrons, I just write one, but there will be many, and positions of all ions, right? Again, no objections, no surprise. So, best thing in the class, most important investment to your future life will occur in next 30 seconds. And because there is not much place, I will write it not horizontally but vertically, this way. Why don't we consider that dipole is an operator and positions of electrons are position operators of electrons, and those are position operators of ions? On one hand. On another hand, I will remind you when will be most important. Now, one little more preparation step. We can assume that electronic and wave functions are split. Electronic are factorized. Electronic is positions of electrons times ionic as function of positions of ions. So phi and chi. Okay. If we affect the molecule with light, the wave function will change. So there will be wave function for ground state and wave function in excited. And the measure to assess the ability of molecule to transfer from ground to excited state will be to take a matrix element of the dipole operator from between ground and excited state. Will be mu to G. G. So matrix element of dipole operator. If you want to be very, very rigorous and start from beginning, you can put electric field here and tell that we are finding matrix element of light to matter interaction. Right? But electric field is classical, and we can move it out of the brackets. So rigorously, it is light to matter interaction. Most important investment in your future career is completed. This is something that is applicable to, in one or another form, into any area of physical chemistry. Whether you do X-ray diffraction, nuclear magnetic resonance, UV spectra, infrared spectra, this paradigm of matrix element of light to electromagnetic wave to matter interaction will enter theoretical description of any type of materials characterization. Right now we are making an example of UVVs of molecules, but it is very, very general. So, what do we do next? I don't know what I'm going to show, what was planned here, but the thing that we separated nuclear and alternative degrees of freedom is known as Born-Oppenheimer approximation. What you may hear is golden rule. Give me a little sign if you never heard this expression. Give me a sign, you can do it if you did hear about Fermi's golden rule before. Okay. You know, but you know who Fermi is. Who Fermi was. He made the first, it's a nuclear physicist who made the first working nuclear reactor in 1942 in Chicago. But although he was director of experimental projects, he's mostly theorist. So if you do theory, you can affect experiment. The Fermi's golden rule is the simplest possible equation he ever wrote. So the rate, and in your project you were exposed to the rates. So rate of transition from electronic state 1 to electronic state 2 is proportional to matrix element of wave function 1 to wave function 2 absolute value square times density of states for states type of states 2 if they do exist, if there are multiple states, and to make it right dimensions divided by Planck constant. You will see it, I promise. Even if you do not select research career, if you do industry or teaching, you will see this equation. And it works for most of processes at the very initial time step or in the limit when the interaction is weak. So I have about 15 minutes, is that right? Less, 30. So, you already went approximately over Born-Oppenheimer separation. One can go into more details, but it is not the most critical thing. So we need based on Fermi, based on Fermi's golden rule, we need two things to assess intensity at which light promotes ground state into excited state of a given molecule. So we need matrix element of this light to matter interaction, and we need density of states which will be replaced to resonance condition. So the final states will be accessed only if the frequency of the incident light will match the energy difference of those. So why don't we believe that ground and excited potential energy surfaces are parabolas? For small elongations, it's always true if the molecule is non-dissociating. If they are parabolas, they are quantized. And one can count states 1, 2, 3, 1, or 0, 1, 2. Right? Then the energy of each vibrational state will be 1/2 h bar omega plus m capital h bar omega, where m is index of the quantum state of the vibration. Then the energy of the initial and final state can be computed as here. Excited state electronic energy plus energy of the addition to energy due to fact that it can be non-ground vibrational state. It is a little bit excited in the vibrational degrees of freedom. So m times h bar omega vibration. And for ground also energy of ground state plus it can be different number of vibrational excitations, right? So unless we are at the 0 Kelvin, we can be away from ground state. And for excited parabola, we can access higher than 0 vibrational states naturally even at 0 K. So energy difference is contributed by two factors, electronic and vibrational. Okay? Not a surprise. Easy thing. Resonance condition and matrix element squared. Minutes. So you have a product of electronic state and electronic wave function and vibrational wave function, electronic wave function and vibrational wave function. If we compute it and take it square, it will be what we need for the rate. If we carefully plug in the electric dipole operator, and we assume there are certain approximations that nuclei move so slowly that positions of nuclei will not change on the time scale of irradiation by light. Therefore, we consider those frozen. So only electronic degrees of freedom will affect this optical transition. So here we have a dipole which includes electronic operator of electronic position, and in respect to nuclear degrees of freedom, it will be identity operator, nothing changes. So electronic, nuclear. Then this, and then we integrate over electronic and nuclear. This integral splits on two parts. Electronic and electronic goes to the left. Vibrational and vibrational go to the right. For electronic part, we have position of electron in between. For vibrational part, we have identity operator, nothing in between. But this long combination contributes to ability of a molecule to absorb light. So here we would have the same thing as we would have for knowing nothing about nuclear motion in epsilon nuclear reorganization. Orbital for ground state or wave function, orbital for excited state, matrix element. Easy. With some effort we can do it. But here is a very interesting and interactive thing. It is an overlap of the wave functions in the initial and final states. Since the parabolas are offset, it is overlap of the wave functions centered, not in one parabola, but in different. So even the ground state of the oscillator in the upper and lower parabola, since they are offset, their overlap can be negligibly small, right? So they are offset, and the overlap of chi with index 0 and chi with index 0 for excited and ground can be negligibly small. But if you go to higher orbitals that protrude to this region, the overlap of nuclear wave function can become non-zero. So this overlap of nuclear wave function is referred to as Frank quantum factor. This is critically important for molecular spectroscopy, for UV spectroscopy of molecules. No questions? Yes.
So one question on that. So is that just trying to say that the probability of exciting from ground to ground is small, but ground to an excited state is higher?
Exactly. Perfect. Yes. For molecules. So same figure we already did. So it is electronically ground, electronically excited, G and E, and those are chi functions for ground, chi functions for excited. And it is just repetition of the same figure. And it is drawn for non-zero reorganization of interatomic distance upon excitation. Now, another thing that may impress you intellectually. Suppose that excitation happens at ultra short time, when nuclei are not moving. It means that if we photoexcite system and atoms are not moving, that the whole shape of the nuclear wave function for ground is promoted up, projected up. So it will be the excited parabola will be in the Gaussian state, which we know from coherent state, from oscillator. But this Gaussian coherent state will stay away from the equilibrium. So if you release it, it will start moving. And if you want to express it in the basis of the discrete states, we know how to set it up. We just use expansion for coherent states. So in the excited state parabola, we take different number m harmonics and assign them with the factor that correspond to coherent state expansion, where the alpha parameter will be found from the offset, will be proportional to the offset of the equilibrium positions. We are, I'm not sure if there will be time in class, but now we are coming to the exercise of the table. So here is the offset of these positions. Here is the alpha through proportionality, frequency, mass, h bar, square root. Right? And here are the things that we need to some sense summary. So Frank London factor from ground in the ground to state number m in the excited, because we assume zero temperature, will be overlap of the state m in the excited and state zero in ground. But state zero in ground can be recast as a coherent state with this expansion coefficients, where we know what is alpha, and the creation operator applied m times to the ground state. And if we need a spectrum, which means response, how intensively the molecule absorbs light, we assassinate through Fermi-Golden rule. So the matrix element, which includes all these things, times the resonance condition. Good. So numerical values. In some of your codes, it was about this. Omega, like 1/10 of electron volt, and mass is 12 masses of hydrogen, like approximately carbon mass, 24,000 atomic units. If you plug it all in, then alpha will be about 2. So case study of typical situation for molecular spectroscopy. You're following, right? So this alpha parameter. Now, I'm going to fill the table, and you may try to fill it independently. So alpha equals 2. And we need different states in the excited parabola. 0, 1, 2, 3, 4, 5, 6, 7. We need up to 7. There is not enough lines, but so delta E, we can just tell like delta energy electronic plus h bar omega plus 2 h bar omega and so forth. Here we need to replace this alpha to 2 alpha to 2 in each of them, alpha and m replaced to 0 and 0. So 0 factorial is 1, alpha to the power of 0 will be 1, and e to the power equals to the e to the power 2 squared. It's very close to actual 0. For the second, here 2 to the power 2 divided by 1 factorial. So e minus 4 times 2 to the power 2 will be 4 divided by 1. So it's a little pain without calculator, but I did it at home. Maybe next generation of the chemists will do it as a homework, but let me show the output, because we have not much time. So if you carefully process this fraction, you'll see that the power function raises, but factorial raises too. And at some point, so initially, the values of this Frank-Cohen factor increase, but after some value, they start to decrease. So the higher the m, the value of Frank-Cohen factor will become smaller. So it is an interesting function which goes up and then down, discrete function. So let me watch here. You can remove this e to the power 4 factor and put just 1, 4, 8, 10, 11, 8, 6, 3. Can you recall, remind me this sequence of numbers? So 1, 6 comes up to 10, 11, and then 6 and 3, right? And then we add the delta function of delta energy minus h bar omega, which can be approximated as a little Gaussian. Then we, same as we did for density of states, we dress each line with a profile. So if we increase the temperature, these Gaussian profiles will become thicker and thicker, and they may coincide. But if you explore realistic spectra of diatomic molecules and any chemical molecules that have soft bonds, you will see this substructure to main transition. Even if only one electronic transition is involved, there is not just broadening, but there is an unsymmetric form. So from zero offset, it is shifted to the blue, so to higher energy. So it is blue shift. It's just blue color. Blue shift. Once again, if you excite molecule, you see blue shift. If the molecule is emitting the same molecule, it experiences the red shift. And the difference in the average transition of the center of the distribution for absorption and emission is referred to as Stokes shift. So average transition frequency for absorption and emission do not coincide. Why? Because there is a nuclear reorganization. Here's what I did before. And I congratulate you with completion of academic part of the course. Meeting is dismissed. I look forward to see you tonight if you need help with videos, and I'm very curious to see your presentation on Friday. Please don't forget to submit slides by Thursday midnight.
The internet online was like 3.002. I didn't say 0%. Okay. Yeah, it's in the last. Okay. Should I really locate? Okay, good. Because I thought it was wrong. Class I thought.
I mean, everyone showed up.